Today we are going to do a quick study of Lenz law levitation. Here we have a wire pancake coil of about 1,000 turns, 0.5 millimeter wire. We hooked it up with these two wires to a voltage controller over here and to an isolation transformer for safety, which will put 240 volts in, or any voltage we want really, at will. And then we take an aluminum plate, which is 3 millimeters thick and 150, a little bigger than the coil. And we put it on top of it, and then when we turn on the power like this, the coil jumps up in the air. The reason is, when the AC magnetic field flips back and forth in this coil 50 times per second, 240 volts, it creates repulsive magnetic fields in this aluminum sheet that lift it upward. They curl one way and then the other. Next, let's see what happens when we have this 150 millimeter aluminum sheet and we stack other 100 millimeter aluminum sheets on top of it. We start with it here. We add one more and it still floats. Another. So it can float really quite a large and heavy weight. These are all 3 millimeters thick, so the total thickness there is about 15 millimeters. Next, let's see how the thickness of the aluminum, or in this case copper, affects it. We'll take 80 millimeter copper sheet, only 1 millimeter thick, and put it over the top. It hardly lifts. But if we put one the same size, 80 millimeter, and 3 thick, it lifts quite a lot. Otherwise, if we put 100 millimeter, 1 millimeter thick, it hardly lifts. But if we put, this is actually 110, 3 millimeters thick copper, lifts quite nicely. So what we've learned from this is, contrary to expectation, the thicker sheet levitates more strongly than the thinner sheet, and the reason is the eddy currents are thicker in the stronger in the thicker sheet. Final demonstration of the physics. We're going to take a 200 millimeter sheet of aluminum, which is 3 millimeters thick, and put it over the top. Floats up quite nicely. But if that aluminum sheet has any kind of cuts in it, like this, it won't float at all. Or if it even has curve cuts, it won't float at all. Whereas the intact sheet of exactly the same thickness floats nicely. So what we learn from this is the eddy currents from this AC copper disc take big paths around the aluminum sheet. First they go that way, and the next cycle they'll go that way. And if we put cuts in the sheet like that, the eddy currents can't flow and it won't levitate. Even spiral cuts, it won't levitate. It has to be a full sheet so the currents can flow to make it go up or down that way over this coil. Next, we're going to test Lenz law levitation by a 100 millimeter commercial electromagnet. First, I'm going to put a 100 millimeter aluminum disc over it, 3 millimeters thick, and turn on 240 volts AC, 50 hertz. Jumps up. Now I'm going to put a 150 millimeter disc over it, a 3 millimeters thick aluminum, 240 volts AC, jumps up. Now I'm going to put 200 millimeter disc aluminum, 3 millimolar thick, jumps up. Now I'm going to put all three of them together like a pyramid over it and watch what happens. Levitates quite nicely, doesn't it? And that's Lenz law levitation by 100 millimeter commercial electromagnet, 240 volts AC. A final thing we might wish to consider as an important detail is that the fields created by this pancake coil, about 100 millimeter, are attractive in the middle. Say the North Pole is facing up there, but on the outside the North Pole is repelling, and it's the South Pole that faces up. So on the outside you have the South Poles facing up, in the middle the North Pole is facing up, and if you try to put the South Pole there, it repels and flips to north.